turn it. I'm not a rock star. Is that okay?
Yeah.
Yep. Okay, perfect. Okay, let me get started. So the first thing I want to talk about is the DT constellation. What is that? Who knows this figure from Tao et al. Of the 5D digital twin model? So there's data in the middle, there's a physical entity, a virtual entity, and services. I'm going to talk a lot today about services. The problem is, it's a good representation. It has more citations than I ever will. But the way I think about a digital twin is I think about it like this. I like this representation. Why? Because you actually get the loop. You get the loop of the data and the actions and the insights. You get the physical twin, digital twin constellation, services at the top, and the models of data on the bottom. And you get this thing that we've been calling enablers. What are enablers? It's computational components. And it's because we want to link the models and data to the services, and we want to see the links between it. So where is this from? This is from a systematic reporting framework that we've been working on, also with Claudio and Santiago Gil from Aarhus. And in this reporting framework, we talk about 18 essential digital twin characteristics. So for example, the services, what are the automatic actions? Because that's very important to tell whether it's a digital twin or not. Fidelity and validity, the timescale, evolution, hosting and deployment, and some others. I can talk about this in the Q&A if you're interested. Okay, so looking at this constellation, I've seen different approaches for digital twin engineering, and many of them start on the bottom layer, which I'm not saying is wrong. You have to do it. You have to talk about the models and the data and get into the technical details. But I'm proposing here, we're proposing to focus on this as a constellation and to start with top down from the services. So let the user pick their service and then start recommending components going down the layers and really guiding them to do the selection, guide them to do the modeling, and get them all the way from the service to deployment on a machine. And what I want to say is I want to scope this and talk about non-software engineering experts. So at Polytechnique Montreal, there are lots of professors, mechanical professors, industrial engineering professors. They know their topic, they're experts in their domain, but they don't know software engineering. So what I want to do is I want to give them something that's approachable and easy for them to use. So, and just to say, this is a work in paper, and it's exploratory application of this vision, and find the edges and find where it works and where it doesn't work. Okay, so talking about the use case, wind turbine testing. This is with Aarhus, Oslo R&D Test Systems, and LARC. And so the large system is really large machines, wind turbine testings. And then what we're looking at is a digital twin for a representative test bench for bending and torquing the turbine pieces. So the blade and the nacelle, the engine. The problem is that they want to focus on is detecting the mismatches between the model of the dynamics and the test bench, because if those differ, if the test bench and the simulated model differ, then that can actually cause structural damage. So we want to detect that as quickly as possible. So on the top here, you see the digital twin. So we want to have this test service, and here's the simulated coupled model. Here's the device under test, which would be the nacelle, and then the test bench, and then there's some wind loading on that. So again, those alerts go to the operator so they can stop that testing process. So building the digital twin, here I'm instantiating that figure I showed before. We have the physical twin with the nacelle, has some actuators and sensors. And then we're going to build up the digital twin constellation and say, okay, we want to have that conformance monitor service. So we need a simulator, and from that simulator, we also need all those models. We need that data, the angular positions, velocity, the test bench model, and the nacelle model. So that comes, the data will come from our physical system, and we'll use these enablers to get that data and also send some warnings over to the operator. So again, from the description framework, I want to see diagrams like this to clearly explain what a digital twin, what it does. In this case, it's actually a digital shadow because it's not, as of yet, Claudio is working on it right this minute on implementing it so that it will actually stop the machine when there's an alert. Okay, and then with the service the service engineering, we want to say, okay, you start with the conformance monitor, and then you might also want to add some real-time visualization, add a dashboard, and that's also going to use some data and models down there. Okay, so the proposed approach, it's a few different pieces. What we said here is, can we define a menu of services for digital twins? How can we use those once you have selected the service? How can we get some recommendations for what enablers and models do you need? And then there's this other side. Once you have that, can we guide the user through these workflows to develop the models, to deploy those models, and then test everything as a service? I like this way of looking at it because it turns into a nice V model going from the top of abstraction down and then back up again with some testing. And we also need to support this with some ontologically aware tools. Okay, so for service selection, who has read the survey by Dalibor? This is a fantastic, fantastic survey. Thanks, Judith. In Andreas's group, it's state of the art. And what we have here is we have some nice big groups of things to do with a digital twin. Okay, who knows the Digital Twin Consortium DT capabilities table? Okay, this one is also good. It's good because it's a little small, but it talks about the capabilities of the digital twins. And looking at these two, I think that they're getting towards what we're proposing, but they're not exactly at the right level of abstraction. I think we still need, as a community, Istvan will probably do a literature review at some point to find exactly what is the menu of services that we want. Future work for him. Okay, ontological basis. So what have we done? This is from Eduard, who did most of the ontology building. We built it in the ontological modeling language, which is part of the Open Caesar framework from NASA JPL. I can also talk about that in the Q&A if you want. What I'm going to show you is a selection of the ontologies. What we have is we have 42 concepts. We have 25 relations. It's too big to show. So I just want to show you the core. And the core is we have that digital twin constellation. We have some services and enablers. We also have some rules here, and that's part of the DT rule ontology. We also have here on the left, we have another specific ontology with artifact simulators, deployed models, getting more into the technical details. And then what we have there on the right is that we have concepts in our ontology for a process, pardon me, the process and some steps and their relation. Again, this is just a selection of some of the concepts in there. But what's important is that we have these ontologies so that we can start linking both the technical details on the left and the constellation in the middle and the process information on the right. I think that sometimes in the models community, there could be more modeling of the process. Okay, so then from the role recommendation, I'm going to show you just a very, very small example that we did for the use case. What we want to do is we want to store those recommendations in a knowledge graph, and then we want to recommend the roles for those models to be found or created. And then we'll connect them to the workflows. So very, very simple. If you want a conformance service, then you're going to want to have a simulator. Then you want to be able to put something in your data role and your nacelle and your test bench. And then that test bench role will be connected to a test bench process that they will follow. So what we can do is we can query the knowledge graph to find, what roles aren't yet filled and recommend to the user, okay, we'll find something or create it with a process. And I think what's really interesting is in the future, connecting this to repositories. So can we automatically find a test bench role? Does that exist somewhere? And then look at additional role constraints and say, okay, well, do you have a test bench role? What's the validity? What's the fidelity of it? Do you have a high fidelity enough model? Okay, and then looking at the workflows. Again, workflows as guided steps give these non-technical experts some guidance to do this, to find, model, test, and deploy components. Again, this is modeled in the ontology. And what we're doing here is that we're meeting the users where they are and enacting this in a Jupyter notebook. Okay, it's very low tech by our standards, but they know how to use it and they're familiar with it. And what are concepts here in the ontology? We want to do steps, decisions, artifact production and consumption, and simulation steps. And really, this is model management, connecting all this, but we need to have this traceability for the user so that, they don't have to look up models and make all those technical decisions, but it's like, okay, we have it stored and we can automatically load things for them. And I'm going to say that I'm going to show you some steps and some stages. These are relatively coarse because we found that really defining very small workflow steps was very rigid for the users. So we're going to work on the levels of detail for them. Okay, so workflow examples. I'm not going to show the Jupyter Notebook itself, but I'm going to show some examples of the diagrams that are involved in it. First, I'm going to talk about the model development and deployment workflow. So this is the coupled model. So this is all of the model elements together. And as we talked about before, we're going to have to recommend to the user, okay, well, you're going to have to decompose that. We need those to be separated models for the digital twin for the conformance monitoring. So in the Jupyter Notebook, we recommend this step. And we say that, okay, we need to test for that decoupling error. Because as you go from this to this, now you've decoupled it, but now you've introduced error. Going further, we recommend, okay, well, now you need to encapsulate things as submodels in Modelica, and then you have to do test for the shared variables. Then you package things as FMUs and making sure, okay, well, we're doing FMI support. Does that work? So we're guiding them step by step. How do you get from that model down into the service? Place the FMUs in co-simulation. So is the co-simulation, is that orchestrated? Is it okay? And then from there, and sorry, this plot is just to show that there's not, the error is relatively small. Then another service deployment workflow. Injecting faults into the test monitor. So that's testing, does your monitor actually work? Packaging it as a service. So here we have the service, and it's just using some CSVs as inputs or outputs, but it's making sure that the data can run through it. We're connecting with the actual simulation. So this is testing for real-time capabilities. And then we're connecting it to the actual physical system. So this is the full test of the system. Again, we want to guide the user all the way from a model down into testing and then into deployment and deploy it to a machine. And how do we deploy it? This comes from Claudio's group, the Maestro engine, which uses FMI and Docker and RabbitMQ for the connection component. And yes, we're making technical decisions for the user, but it's convention, not configuration. We want to give them something easy to start with and give them a running digital twin as quickly as possible. Okay, and then talking about ontologically aware tooling. Again, in the Open Caesar, that's where we have our knowledge graph, and there's a Shiseki server which loads and you can query against the knowledge graph. From our knowledge graph, what we want to do is we want to build the Jupyter Notebook skeleton with the different cells inside. And then those different cells, it will query the knowledge graph. They will perform their steps and test the model inside. And then it will keep track of the data and insert it into the knowledge graph again. So just to show, again, I don't want to show the Jupyter Notebook itself because it needs further development, but just to show a flavor of what we're actually storing in the knowledge graph. This would be in a load step when you actually need to load a model. We want to create new steps node, connect to previous step related to our workflow, create a simulator, add a time step, have a path to simulator, and again, to generic workflow. So it's a lot of technical, detailed traceability information that we want to have automatically in the Jupyter Notebook. So they don't have to worry about this, but we're keeping that traceability for them. Okay, so in conclusion, I've proposed a vision for developing DT services, starting from the top, starting from a selection, going down through recommendations, and then providing the user with ontologically based workflows. I've shown an application to a conformance service. And I think the takeaways is that we can really leverage digital twins for non-technical personnel. The engineers at my university are very excited when I say I work in digital twins. Automatically, they say, we want a digital twin. Okay, there's a lot of excitement here. So I think we can look at these constellations and as experts think about, okay, well, we have models and simulators and enablers. We know how to connect these things. And there's so much semantic richness. There's so much domain knowledge in these services, in these models. We need to leverage that. And then use ontologies for this heterogeneous, flexible, rich modeling as we saw before. And we can use it for model management too, and really get this, as we saw in the last presentation, these detailed webs of domain knowledge and technical knowledge together. And the practitioners, they're already used to Jupyter notebooks. So let's use that. Let's give them these roles and these recommendations, these workflows in the notebook that they can use. And as future work, I'm very excited to work with the practitioners and to improve the richness, to say, okay, well, what roles do you need for each service? What workflows work for the service? You know, how do you get the variability in there? And then to validate this approach. So I'm ready for all your questions. Thank you very much.